180 liters of fluid filtered each day. Less than 1% is lost as urine.
Sorry.
Yeah.
So 1% of that would be 1.8
Natalie told me that
liters.
suicidal person.
On the high end, we're looking at 1.5 liters of urine produced each day. So 180 liters of plasma is the equivalent of filtering your entire plasma volume 60 times a day. More than 99% of that volume is reabsorbed. That's going to require a lot of blood flow to form all that filtrate and a lot of oxygen to process all that filtrate. Right? Lots of active transport when it comes to reabsorption. So it's pretty impressive that these two small organs, roughly the size of a large bar of soap, consume up to a quarter of your cardiac output and up to a quarter of your oxygen supply. In the big box is breaking down the basic function of the kidneys to very specific functions. Right? The basic function is regulates composition and volume of ECF. More specifically, that includes ion composition, volume of plasma. Among the ions, sodium and chloride, which account for nearly 280, 290 of the 300 milliosmoles that constitutes the osmolarity of our ECF. So those two things are related, ion composition and osmolarity. And osmolarity and volume are connected, right? If you want to keep extra volume in your bloodstream, you've got to put some extra salt in there. Because water is simply going to follow solutes. So ion composition, volume, osmolarity, all connected. Also connected to ion composition. Two specific ions, hydrogen and bicarb. And they together will dictate pH of the ECF. So if our pH is decreasing because of lactic acid formation, because we are consuming an acidic diet, then that means on a daily basis you are experiencing net gains of hydrogen. You're making them metabolically, you're consuming them from your diet. So you would have to have net excretion of hydrogen ions on a daily basis to keep up. Does that make sense? So on average, is your urine acidic, alkaline, or neutral? Acidic, because it's carrying out with it all the excess hydrogens, all the excess acid that we are producing or consuming or both on a daily basis. The average American has a rather acidic diet. Removal of wastes. That includes the nitrogenous wastes, uric acid, urea, ammonia. Anything that comes into our internal environment, typically through food and beverage, right? Think of all the preservatives, pesticides, all the various chemicals that are in our foods. Things that may or may not harm us, but either way, don't have a use for us, right? If it's not useful, we're going to get rid of it. If it doesn't have a purpose, it needs to go. So there's a lot that we're excreting on a daily basis. And while doing all that, we try not to lose nutrients. So the kidneys do their best to reabsorb as close to 100% as possible for all the different nutrient types. To get an idea of the urine composition, what is normally found in the urine and how much, you have urinalysis tables. You can check the appendix in the textbook. It's going to be similar to this table here. Just FYI, just to give you an idea of what's in there and how much. Nothing you need to memorize here. So if you're looking at wastes, you would expect the amount found in the urine to be quite large. So lots of urea, creatinine, ammonia, uric acid. Urobilin and bilirubin from the breakdown of hemoglobin. Nutrients you would expect to be quite low in comparison, like 0.11 grams of carbs, 0.21 ketones, 0.02 lipids, 2.25 amino acids. And then next to the gram output is the concentration in the urine. Now these are really small, micrograms, right? Not milligrams or grams, micrograms. So very low levels. Sodium, chloride, potassium, calcium, magnesium, this totally depends on your diet. Someone with a high salt diet is going to be excreting a lot of salt on a daily basis. You'll find a lot of salt in their urine. If you're on a very restrictive salt diet, because you have high blood pressure, for example, you may be just taking in what you need and would be therefore excreting very, very little. So those numbers are quite variable. Depends on the person, depends on their diet. Red blood cells, white blood cells, you would expect to find none in the urine, but the filtration membrane is not perfect. The occasional protein gets through, the occasional blood cell gets through. But all in all, these are very, very small numbers. Now we're looking at fewer constituents of urine here, but the nice thing about this table is it compares urine to plasma. So if you're looking at nutrients, you would expect plasma concentration to be really high and urine concentration to be very low. Glucose is near zero. There is a tiny bit that ends up in the urine, but not much. As opposed to 100 milligrams per deciliter, which is the standard units they're working with. Lipids, 0.002 compared to 600, so very little getting lost in the urine. Amino acids, 100 compared to 4.2. That should seem really strange to you. You should not have more in the urine than you do in the plasma, and you don't. Do you see what they've done here? It took me a minute to figure this out first time I saw it. I thought it was a typo. They changed the units on you. So this is 4,200 mg per deciliter versus 100. 100 versus 4,200. Right, so very little amino acids in the urine compared to plasma. This is 62 compared to 7,500 mg per deciliter. Right? But then they just randomly decided to change the units for those two. Didn't even mention this one. This is grams per deciliter as well. When they start off by saying, oh, the units are all mg per deciliter. And then they throw that wrench in there. But as long as you understand what they've done, it's okay, it makes sense. And then down here, nitrogenous wastes. It's the opposite of nutrients, right? Wastes are going to be really high in the urine and relatively low in the plasma, as you would expect. Ions, it completely depends on your diet, how much you're going to be excreting on a daily basis. Other functions of the kidneys outside of regulating composition and volume. 3 chemicals are secreted: EPO, renin, calcitriol. Calcitriol is not secreted per se, but synthesized in part in the kidneys. EPO and renin, they are secreted from what cells? So now we know the name. G cells, also known as granular cells. And then it turns out that gluconeogenesis, which is primarily carried out by the liver, also occurs in the kidneys in response to starvation. But there's a lot more carried out by the liver. That's one of the liver's main jobs. Since blood cells cannot pass through the filtration membrane, only the plasma of blood is filtered. Right? So you got to take whole blood and subtract from it the hematocrit, 45%, leaving you with 55% plasma. It is the plasma that becomes filtrated. So if the kidneys receive 20% of your cardiac output, and let's say your cardiac output is 5.7 liters per minute, you should be able to figure out how much blood is flowing through the kidneys, and then from that to figure out how much plasma is flowing through the kidneys. And once you have that figured out, you should be able to calculate how much of that plasma becomes filtrate. In other words, you should be able to calculate filtrate formation. So I have the math on the study guide to walk you through the process. We start with 5.7 liters per minute and multiply that by 0.2 to get RBF. What is RBF?
Renal blood flow.
Renal blood flow. Why did I multiply cardiac output by 0.2?
That's what the kidneys receive.
Because the premise is 20% of your cardiac output is going to the kidneys. So now from that cardiac output of 5,700 mils per minute, 1,140 is going to the kidneys. That's your renal blood flow. Next step, convert your renal blood flow to renal plasma flow. Because in the end, that's what becomes filtrate, the plasma. So you multiply that 1,140 mils per minute by 0.55, right? Because 55% of whole blood is plasma. 0.55 of 1,140 is 627 mils per minute. Now to make the math nice and easy, I rounded the 627 to 625. And that makes the next step very, very easy. How much of that 625, how much of the renal plasma flow becomes filtrate? In other words, what is the filtration fraction? 20%. So 20% of your renal plasma flow becomes filtrate. So how do you calculate filtrate formation? GFR, glomerular filtrate rate. 625 times 0.2. And that's why I rounded it to 625, because what is 0.2 of 625? 125. 1/5 of 625 is 125. So that is the rate of filtrate formation. 125 mils produced every minute, based on a renal plasma flow of 625 mils per minute, which is based on a cardiac output of 5.7 liters per minute with 20% going through the kidneys and 55% of that being plasma. And 125 is the number. That is the most common reference value from the textbooks as far as what GFR is and what we're trying to maintain. So you should know that number. We're always trying to keep GFR right around 125 mils per minute. And the key to doing that is to keep net filtration pressure stable. If your NFP is nice and stable, then your GFR will be nice and stable. Overview of urine formation. What are the three basic processes? What's step one? What's happening in the renal corpuscle?
Filtration.
Filtration, right? Filtrate formation. And what is a typical glomerular filtration rate? A typical GFR? 125 mils per minute. So as that filtrate passes through the renal tubule, and obviously this is a physiology image, because this is not anatomically correct by any means. This single tube right here is representing the PCT, plus the loop, plus the DCT, plus the collecting system. This is everything. But what it is showing you is, and this part is anatomically correct, you do have blood vessels that run alongside the tubules. They're called paratubular capillaries. If you're pulling something out of the filtrate, moving it across the tubule cell, through the interstitium on the other side, across the capillary wall and into the blood, then you just achieved reabsorption. If you take something that's in the paratubular blood, across the capillary wall, through the interstitium, across the tubule cell wall, into the filtrate, that is secretion. Those are the three basic processes. Starts with filtration. And then once you've got your filtrate flowing through the renal tubule,